Hey everybody, we are here to talk about the Spring Force Lab that you guys worked on last week. So here is some example data that I collected from the PhET simulator, probably similar to you. I have the weak spring, that is I had it on like the one value. This is my data, and you can see I plotted it here, here, and here. And so when I do my line of best fit, I get something like this. And for the strong spring, that was 10 all the way. My data was here, and my line of best fit was something like this. And when I do the math, I get that the slope of this is, for the strong spring, was about 12.5. The units would be newtons per meter, coming from the newtons and the meter on my graph. And the slope for the weak spring was 3.1-ish, with some rounding, newtons per meter. Now, if you use the same numbers that I did, the 1 and the 10, you might have similar numbers as well. And so I want to talk about what this means for this lab. So now, first of all, one of the things that you should notice, now we only had 3 data points, but you do notice that these are going to be linear. The relationship between the force that the spring exerts and the amount of stretch. And so because the force of the spring and the stretch, because this is linear, we can actually write and make this into equation. And we will, of course, use y equals mx plus b as our form. Y is the force of the spring, and x is the stretch. And so now we just are looking at the slope. And the slope is something that is actually called the spring constant. So force of the spring is going to equal this slope, which is the spring constant, times the stretch. Now, if we wrote this in variables, it would just be Fs equals K times the stretch, which we are going to abbreviate as delta X, because that is the amount the spring is stretched from its natural length. So we have our springs without any masses right here and right here, and when we added mass or a force to it, that spring increased in length. And so that change of L is what we're talking about when we talk about stretch. So let's talk a little bit about spring constant. Spring constant is the relationship between the amount of force it takes to deform a spring, in this case, 1 meter. We could have picked any amount, but we're going to choose 1 meter. And so the units for spring constant, which is abbreviated as K, are newtons per meter. So if we look at the spring constants that we have for the strong spring, we said K was 12.5 newtons per meter. That means it takes 12 newtons, 12 and a half newtons are needed to stretch the spring 1 meter. And similarly, it takes about 3.1 newtons to stretch the light spring. So it takes less force to stretch the light spring than it does the heavier spring. And so that's what the spring constant is. It tells us the relationship between the amount of force needed to deform, in this case, deform, we're talking about stretching, but we could also be compressing. Meaning make it tighter together. How much force is needed to do that. And we get this relationship, the force of the spring equals Kx. This has another name. This is also called Hooke's law, named after Robert Hooke, the guy who studied all about cells earlier as well. So he did a lot of things and got this relationship named after him. So let's talk about this in let's just do a couple problems with this. So hold on, let me pause this.